SPEL is located right throughout Asia Pacific, and these little stars here on the map of Queensland show the floating wetland projects that we currently have installed, and I'll give you some very quick pictures of those. What I'm going to show you today is absolutely nothing new. Floating wetlands are a naturally occurring phenomena, and some of you may have been to Lake Titicaca in Peru, where the Peruvian lake people actually live on naturally occurring floating wetlands. This is a cross-section of one of the naturally occurring wetlands in Peru. You can see it's about 800 mil to a metre thick. It doesn't start off that thick. Over time, the organic matter in the plants dying and regenerating, seeding and growth, the organic matter keeps building up, and so they get thicker and thicker. The Aztecs and the Incas, there's evidence that they used floating wetlands for treating their wastewater thousands of years ago. So it's very, very interesting. And I didn't know until I did a trip to Mackay with some of the Great Barrier Reef people a few months ago that Australia has its own floating wetlands in Tasmania. So that was a fun fact for me. So what do man-made floating wetlands look like? This is a system in New Zealand that was put into a stream to treat phosphorus loads coming off an apple orchard. It's 6 months old there. And this is what it looked like when it was 18 months old. And I'll show you some photos later on of older systems. So I sort of depicted that as a cane farming channel, and you put the wetlands on there and we can remove some of the pollutants that we're talking about. This photograph here is our oldest system. This product was originated in America, and this system is now 18 years old, not 17, like it says on the slide. It hasn't been touched or weeded or anything from a maintenance perspective. It looks really good. Having said that, it depends on your catchment as to what you have to do as far as weed management and that sort of thing goes. You can see a bit of the matrix around the edge here. We've had some plant die back and it just hasn't come back again. So we've been testing these systems in New Zealand. The product that we do for Asia Pacific is manufactured in Auckland at the moment. And we've done a lot of research with Dr. Chris Tanner from NIWA, New Zealand's version of the CSIRO. And you can see published papers from Chris online. Essentially what we're doing is biomimicry. We're facilitating nature to do her treatment principles and processes. And essentially what you've got is a floating trickle filter. The plant roots going down into the water column provides a surface area for the base of your food chain to live on. So the very base of the food chain, those particular microbial species. And then the visible life forms then feed on those. So for the microbes, plant roots being an active living system and putting oxygen into the bottom layer of biofilm on the plant root, it's their version of the Hotel Hilton for free. So we're putting nature on steroids essentially. So this cross-section here shows you a healthy plant root. You can see it's pumping its enzymes, emitting its sucroses. And this brown sludge layer here is the biofilm that is growing on that plant root. Now, if we talk about activated sludge and slip over to a wastewater situation quickly, if you're putting Anox Kellner's discs, for example, into activated sludge, a plastic disc to create surface area, you'll grow microbes on them, but they'll be compact and there won't be much biomass in it because they can't derive anything from the surface area. Whereas with plant roots, being a living system, the microbes actually can take something from the plant. What I've been taught is that if we could turn off microbes and turn off the sun at the same time, like flicking two light switches, it would actually be a race between those two forces as to which one would collapse Earth's system first. So when you put plant roots into a water column, you can support over 3,000 species of microbes. And I say that with authority because we have a partner in Hungary and they're called Organica. And they do this in activated sludge. And for the last 6 years, they've been given €1 million a year from the Hungarian government to do research in activated sludge. So that's where a lot of my numbers are coming from. So we're boosting the symbiosis or the symbiotic relationships in that water column. Hence why I said before we're putting nature on steroids. So what does this actually mean for us? 1 cubic metre of active plant roots gives us a surface area of between 10 to 12,000 square metres. Conversely, 1 cubic metre of blue-green algae has a surface area of 4,000 square metres. So when I'm going in to compete with algae, it's a matter of biological warfare. And so it comes down to my surface area numbers, and when I can put plant roots into that water column, I'm going to win hands down every time. So this is the power of what we're talking about today, and it's the power of nature. This is not something that's man-made. So all we have to do is facilitate her principles and processes. Now, I just want to draw the difference between a floating wetland and a conventional wetland. And I'm by no means saying that a floating wetland is the silver bullet, and it's certainly not the solution to the problem. We have to have a treatment train. Floating wetlands pretty much need permanent water volume. So we're going to struggle with a floating wetland in the dry season. So you have to take that into account in your design. So typically we're getting our treatment in the macrophyte zone in the rhizome layer. So as they were saying before, 300 to 400 millimetres, or you might extend it to 800. So dig that out 1.5 metres deep, because our floating wetland plant roots typically go to 1.8 metres deep. If we're using carex, vetiver grass is much better. We dig that out, and in the same square metre footprint, we're tripling or almost quadrupling our surface area for treatment. So we call this the concentrated wetland effect. Now, how do we make it? It's made out of recycled PET bottles. At the moment, the recycling plant is in America. We crush those bottles back to flake. They go through a manufacturing process, and we use approximately 139 500 ml PET bottles per square metre of floating wetland. Then that's a conservative number. So we bring that recycled plastic matrix down to Asia Pacific, and we cut those rolls up into modules that are 2.3 metres wide and 4 metres long. The science behind that is because they fit perfectly into a shipping container. Each module has 10 aluminium joiner plates. Those joiner plates are connected to their opposing module with a nylon webbing. Each layer of matrix is 50 ml thick, and we have 4 layers of matrix. You'll see there that we've drilled out plant holes. We drill the plant holes 3 layers deep. So each plant, which we're showing over here on the left, goes into that hole, and it sits on 50 mils of matrix. It takes less than 1 week. It's about 4 to 5 days for the plant roots to actually grow into the matrix, because there's surface area in the matrix as well. It's about 200 square metres of surface area per square metre of wetland. So it is an engineered system, but I make a very pertinent point. We are just providing the raft or the platform for nature to take over. This is by no means the end game. Nature takes over this system, and within 4 or 5 or 6 years, on most of the systems, you actually wouldn't know it's a man-made system. But we have to get the water column to come into contact with the root system if we're going to get treatment. So we prefer, a lot of people think floating wetlands, terrific, I want to put it in line. Yes, you can do that, but we prefer to put them offline, because we can then control the flows, we can minimise any short-circuiting, and furthermore, we're working with a very loose and spatial biofilm, which gives you excellent biomass and gives you excellent mass transfer. When you get high flows ripping through there, you lose that biofilm, you lose that microbial activity, and the system has to build up. Having said that, they're quite resilient. We've got wastewater systems in New Zealand that get snow over them every year. So the outer side dies off and the inner core stays. So our treatment rates drop off, but we still treat within the design consent limits. So for the suspended solids removal, it is the biomass or the biofilm that is taking the suspended solids out of the water column. And so when you can control it, we're very, very good with fine sediments, fine particulates, especially clay. Clay in water is, I would describe it like a piece of paper. It doesn't want to settle. It just keeps floating along. So by getting it stuck on the biofilm, we're able to lock it up in the plant roots. But the next thing is how do we get that back out? So when we're working with an offline system, and I'll show you a picture later, with a weir, we have the opportunity to undo the anchor points of the wetland, push it up to one end, and then excavate out that sludge and bring it back. You don't have to reset your asset. So with a conventional wetland over time, it'll get silted up and you have to dig it out, reset it or start again. And then for the nutrient removal, we've already touched on that today very impressively with Dr. Phil down here. We're basically facilitating nature's pathway. And the thing with this floating wetland is you can walk on it. You will get your feet wet if you stand still, it'll slowly sink down, but we can go onto these systems and actually harvest the plants. In Burma and in Thailand, they actually use them to grow vegetables on. So we can actually, and in wastewater systems, we would go on about twice a year and harvest the plants, take that phosphorus away. The reason we do it in wastewater and not in stormwater is simply because in wastewater we have much higher loads of nutrient coming in, therefore the plants get much more voluminous. Whereas in stormwater, the nutrients coming in is much lower and the plants don't react with as much growth. So testing these devices, there's been work done in Canada, in Florida, work in New Zealand, a lot of work in New Zealand, and then when I started to do this product in Australia, I went to the University of Sunshine Coast. There's 4 papers there covering those countries I just mentioned, and that's a picture of the New Zealand one that's doing road runoff in Auckland, and you can read Kareen's paper. And this is our field test site in southeast Queensland at Bribie Island. And I would just like to take one moment to thank Moreton Bay Regional Council for giving us the opportunity to test on this site. And we've got David Meyer from Moreton Bay Regional Council sitting here, so thank you very much. We started this project a little over 3 years ago, and we put the floating wetland on this, what we call Finger Lake 1. So this catchment, to be able to develop this catchment, we had to detain the Q100 flows from the national park next door. So the council was looking at, with the consultant, was looking at the option of 3,000 square metres of biopods scattered around this 544 lot development, or we were modelling with our overseas data that we could do it with 1,000 square metres of floating wetlands. So we did the life cycle costs and it was a no-brainer, but we had to prove that it would do what we thought. So on Finger Lake 1, we put impermeable curtains from the sides of the lake out to the wetland and then down the sides. So all of the flow going into the lake from this catchment is going underneath this wetland. And it's a very conservative approach because we're getting high flows through there as well as low flows. And because of this side inlet here, well, in the drawing it's actually down here, and there's the other inlets down there, we had to position our wetland halfway down the lake. So we're getting a lot of sediment drop out before it actually hits our wetland, which is not ideal for me because less in, less out. So it's quite conservative. So there's your curtains. We wouldn't normally have that on a project, so that's a bit of a one-off. It was commissioned in August 2013. And there's my friend Dr. Darren Draper out on the pontoon. We have an inlet sample, a middle sample and an outlet sample. There's your tipping bucket rain gauge. And we started with a $10,000 flow meter from Xylem, which on their marketing material it said it was designed for drainage channels for irrigation. It was a $10,000 brick. I've gone back to 2 V-notch weirs on the inlets and another one on the outlet. So expensive lesson, and if you're going to try this, just learn from that mistake. So this here shows you 6 months of plant root growth. Those plant roots are now nearly 2 metres long. We've seen plant roots growth in Queensland like we haven't seen anywhere else. And I think it's just because we've got a bit of a warmer climate than some of the other countries we've been working in. So the University of Sunshine Coast has had master students hopping on and off this project, and we've just published our first paper, which has 10 flow-weighted rain events in it. So we did a dye test to make sure our curtains weren't leaking any water. We put rhodamine dye through the water, and we tested it at 100 litres per second and 200 litres per second. Now, bearing in mind that this 100 square metres of wetlands is 0.1% of the contributing catchment. There was no science behind that. I had to fund this testing myself, and 100 square metres is what I could afford to give them and install. And it just happened to be that it worked out to be neatly 0.1%. So over 9 flow-weighted events, our efficiency ratio for TSS is 74%, TN was 40, and TP was 59. Interestingly, on that 40%, 63% of that 40% reduction is nitrate. So we have got the speciation breakdown, but I haven't yet got the PSD curve from the uni. But for Korean-born stuff on the road runoff, her D50 was 63 microns. And I've just been texting Darren to say, hurry up and get in there and tell me before I talk what the 10 micron is. But he hasn't been able to come back to me. So, variable flows, velocities and hydraulic grades. This is a 9-year-old project in Auckland, and you can see the high water mark is there, and it's about 4 metres. So anchoring comes into play. We've used a few different methods over the years, but the cheapest and the most effective is what we call a platypus anchor, which is essentially a spear that we put into the ground that works on the same principle as a plaster wall plug. And we anchor on the sides of the wetland and then back upstream. We have to take into account what the maximum hydraulic grade is to the minimum. So we position the anchors so that the wetland, as the hydraulic grade line rises, will stand up on the anchors. Then as it subsides, it will come back down and it brings it neatly into position. And this project has been doing that for 9 years. So there's your upstream pipe, and there it is at about the 3 metre mark, and that gives you a view of it from downstream. Clearly in bypass. So this system was put in with a gabion rock wall downstream to create a bit of a sump that gave it bank to bank with 1.5 metres underneath it. Bigger velocities. This is a project called Sungai Punggol in Singapore. If you've ever got a couple of spare hours in Singapore, ping me an email and I'll send you a Google pin. This was connecting a hotel to a golf course, and we cut our teeth on this project. We have lost pieces of this wetland to logs coming down the stream and smashing into it, but it's a modular system, and we've just been replacing those. There was pylons involved in the anchoring of that. I'm not proposing anything of this scale for what we're talking about here today, but it's interesting. And this was our dry season project, where we've gone into a detention basin and put a sump in the detention basin for the floating wetland. This project is in Newcastle, and we've done this project with GHD. Typical sediment forebay, but all the water has to go out underneath the wetland. We let it dry up, and the plant roots, because it was drying up slowly, went into the Bethnic zone, which was nice and soft because of the water. Then when the rain came back, it floated back up again. Having said that, we don't want to design for those sort of situations. We want it to be a worst case. And there is that wetland that you just saw on the plan with all the water around it. In sewage treatment plants in Australia, we have to watch out for turtles. I did my first trial with Queensland Urban Utilities, and they said, how about turtles? I said, oh, we've got 23 plants in New Zealand. I haven't had any problems. Out of Forest Hill, there is thousands and thousands of Yertle the turtle in that pond. And plant roots are the most juicy, luscious thing for them to gobble up. So what we did was, we put a stainless steel poly-coated netting in bags underneath the wetlands, and that netting, the salmon farmers use it to keep the seals out of the salmon farms. So on my Clifton project, Yertle the turtle has not got through that netting. The other thing, pests, is birds. If you get the classic old water hen, so we have a few bird netting options where we can do your typical stand, which I like this. This is cheap, and you just take it off after 6 or 8 weeks, or you do a complete netting like this project here. And that just prompts me. I'm talking about fresh water, right, or storm water that we've been working with. They've done 3 successful saline projects in America. It comes down to the type of plant. So we've got a trial in Western Australia and a trial on the Sunshine Coast, thanks to Sunshine Coast City Council. Crispin, thank you. Where we're starting to work with saline species. Now this is 2,000 square metres of wetland at Park Lakes 2 at Bli Bli on the Sunshine Coast. Again, thank you to Sunshine Coast City Council. And there's 2 islands here. I fluked this photo. We have a permanent SLR camera there in a box. Please don't go and steal it. In a waterproof case, and it takes a photo every 5 minutes. And we just fluked that. But see this silt here? That is construction silt loads coming off the site. This wetland is only 8 weeks old, and we stopped all of that silt. They were able to go down there with an excavator and take it out. This is our Gladstone project, and we're offline with a earth embayment and a weir wall at the end. This is where we've got good data on algae. And this is a keynote project in New Zealand. The Lord Mayor got involved in this one, a bit of advertising. It was an offset project where they destroyed a wetland to extend the airport runway. and so they put this in an algae hotspot. But I've got a note there. Based on our Bribey data, 2,000 square metres of floating wetlands can remove 732 tonnes of fine and coarse sediments per annum. There is that wetland fully established. That's 16 months later. And 2,000 square metres can remove 8.6 tonnes of nitrogen per annum, based on my Bribey data. And then we can remove 1.1 tonne of phosphorus. And there is Jed walking on that same said Rotorua Island. So that's in full growth mode. Over time, plants will die and they'll regerminate, etc. So it doesn't always look that green and that beautiful, but at the end of the day, it looks like a constructed wetland. Thank you very much. SPEL is located right throughout Asia Pacific, and these little stars here on the map of Queensland show the floating wetland projects that we